This presentation is related to my paper entitled Nonlinear PD State Feedback Control for Electronic Throttle Valve based on Ant Colony Optimization, written by me, Noor Sabah, and Amjad Ahmedi, as well as Raed Al-Azzawi. We will start with an introduction about the throttle valve, and then the problem statement will be discussed, highlighting the challenges to be addressed. After that, the objective will be set to show what we want to achieve in response to these challenges. The concept of state error feedback will be explained with its mathematical model. The controller design will be examined carefully, covering both linear and nonlinear methods. The results of a simulation will be presented to show how effective they are. In the end, a conclusion of the study will be presented. Today's cars have experienced significant changes to meet the strict emissions and the fuel efficiency regulations. One vital component for achieving these goals is throttle valve, which help control the fuel efficiency and emissions. To adapt the latest motorized technology trends, we need an advanced control system for electronic throttle valve. This paper shows and explores two control methods, linear and nonlinear state error feedback techniques. These methods are enhanced through Ant Colony Optimizer. The throttle valve in a car is a vital component, and it's typically shaped like a circular or oval disc or a plate. This valve is positioned inside the throttle body, which is a part of the engine's air intake system. The primary function of the throttle valve is to regulate the flow of air into the engine, controlling the amount of air that mixes with the fuel in the burning space. There are specific challenges in the throttle valve system, including nonlinearity and non-smoothness caused by friction model and nonlinear spring, uncertainty in the system parameters. The actual behavioral or properties of the throttle valve system don't meet the expected or desired conditions for control. While the goals of the paper is to design a robust and modern controller, address both internal throttle valve issues and external disturbances, achieve precise and consistent control of the throttle opening, ensuring response to driver input within acceptable limits, and lastly, minimizing the required control efforts. This paper outlines the steps intended to take related to the electronic throttle valve system, such as thorough examination and analysis of a mathematical model that describes the behavior of electronic throttle valve system, design state error feedback with two versions, linear and nonlinear, use Ant Colony Optimization method as a tool to select the best gain values for a PD controller. Structure of a state error feedback that was done using MATLAB is showing in the figure. The figure shows the schematic diagram of a throttle valve with obvious springs and dampers surrounding it on both sides. As we understand, a car includes both mechanical and electrical components, hence we will employ Newton's second law to analyze the mechanical section. Similarly, we will utilize the same law to address electrical components and establish state space. Deriving the equations, the following equation is obtained that include theta bar representing the limp open state, which corresponds to the car idle state. In this mode, the throttle remains partially opened at an angle of 5.44 degrees, and the engine operates with minimal fuel consumption to keep the car running. Typically, the controller increases the system order of equations. To simplify and reduce system complexity, we can neglect the motor inductance that has a very small value, nearly zero, and focus on the resistance value, which is significantly larger. This leads to an update of set of equations, also combining all synonym functions and system issues into the term d of t, which will represent the nonlinearity of the system. So d of t in this case will be the total of uncertainties of the system as represented by delta, as well as external and internal disturbances of the electronic throttle valve as represented by w of t. The controller design will be into two types, which is linear that uses normal proportional derivative controller and nonlinear, where x1 desired is the input position and x2 is the derivative of x1, which is in this case the velocity. And the feedback control law of the PD controller is U equals minus Kp multiplied by error minus Kd multiplied by the derivative of error. For the nonlinear case, we will propose using an alternative version of a PD state error feedback control, where the nonlinear PD parameters are designed based on the error and its rate of change, where phi showing is the nonlinear equation with its parameters and Kpn contain the gain multiplied by optimization parameters. We will start at a step input value x1 desired of t equals to 50 degree and the throttle valve angle is 12 degree and applying ant colony optimization algorithm. As observed in the figure that shows the cost function related to the number of iteration, we can conclude that the blue line representing the nonlinear case has quickly stabilized with a minimum error. The showing figure represents the relationship between position and time between desired and actual for linear and nonlinear throttle valve position with a step input value of 50 degree. The results of a linear schema are decent but not entirely satisfactory due to the presence of steady state error after system settles at 64 milliseconds. To address this, we re-optimize the gains for the nonlinear schema, resulting in more acceptable time response specifications. These include an allowable overshoot of 7.7%, undershoot of 3.8%, faster rise time which is 48 milliseconds, and reduced settling time to 95 milliseconds. Additionally, the nonlinear schema efficiently eliminates steady-state error. Now, instead of using step function, the inputs is changed to sinusoidal, which is more realistic, and the following two equations show the input x1 desired and the derivative of it, which is x2. Disturbance is applied where Wt represents the disturbance and the figure represents its shape. The left-hand side figure shows the desired and actual for both linear and nonlinear throttle position with the sine input, and the right-hand side represents the desired and actual velocity with desired sine input. As we can see, the nonlinear blue line is much better and matches the desired input exactly, not like the linear part. The left-hand side figure shows the desired and actual for both linear and nonlinear angular velocities with input x2 and high-frequency disturbance. And similarly, the nonlinear case performs better than a linear one that shows high fluctuations as shown in the zoomed plot on the right-hand side. The figure in this slide represent the control action for the PD linear and nonlinear control law with the presence of disturbance. And nonlinear case works better in all situations, even when calculating the root mean square error as showing in the table, where RMS for the error 1 is equals 0.7 in a linear case, while in nonlinear case it equals to 0.02. In this study, we applied both linear and nonlinear PD state error feedback schemas to the electronic throttle valve system, which faces nonlinearity, parameter uncertainties, and external disturbances. The linear schema has limitations like steady state error and struggles with external disturbances. In contrast, the well-tuned parameters of the proposed nonlinear schema effectively moderate external disturbances and achieve faster error convergence compared to the linear schema. Both schemas employ heuristic search, especially ant colony optimization algorithm for parameter tuning. Simulations, as we saw, confirm the effectiveness of the nonlinear PD state error feedback with optimization controllers. Thank you for listening.